colossal energy release, which can trigger atmospheric ionization and affect the climate. Yet the story of gamma-ray bursts is not solely one of destruction and fear. They also serve as catalysts for learning about the universe's most fundamental processes. By studying these explosions, scientists are piecing together the mysteries of star formation, supernovae, and the formation of black holes. Each gamma-ray burst not only illuminates the cosmic distance between us and the remnants of the early universe, but also reshapes our understanding of the forces that govern the cosmos, unveiling the intricate dance of creation and annihilation that defines our existence. Gamma-ray bursts are incredibly intense explosions in distant galaxies, and they have sparked a lively discussion within the scientific community about their origins. These bursts release more energy in just a few seconds than our sun will emit throughout its entire life, which has left researchers in awe and eager to understand what triggers such spectacular phenomena. The debate centers mainly around two leading theories: the collapse of massive stars and the merger of neutron stars. Within the first theory, astronomers believe that some gamma-ray bursts are caused by the core collapse of massive stars. These stars, often more than 20 times the mass of our Sun, burn their nuclear fuel incredibly quickly. When they exhaust this fuel, they can no longer support themselves against gravitational forces and collapse, resulting in a supernova. In some cases, the collapsing core leads to the formation of a black hole, while jets of energy fire outwards at near-light speed. If these jets are pointed toward Earth, they produce a gamma-ray burst that we might detect across vast distances. The second theory involves the merger of compact objects, specifically neutron stars. Neutron stars are remnants of supernova explosions, and they are incredibly dense. When two neutron stars orbit each other closely, they can eventually spiral in and collide. This collision creates gravitational waves and a burst of gamma rays. Recent observations have provided strong support for this scenario, especially following the discovery of gravitational waves from such mergers, confirming the connection to gamma-ray bursts. Despite advancements in our understanding, the debate continues. Researchers are still working to determine the rates at which these events occur, and whether other previously unconsidered processes might also contribute to gamma-ray bursts. As telescopes and detection methods improve, the quest to fully understand these cosmic explosions remains a captivating frontier in astrophysics, promising new revelations about the universe and its most powerful phenomena. The discovery of gamma-ray bursts, or GRBs, has significantly shifted our understanding of stellar evolution and the life cycles of massive stars. These powerful explosions occur when a massive star runs out of fuel and undergoes a catastrophic collapse. These bursts represent the end stages of a star's life, showcasing a dramatic transformation that was previously not well understood. Before the identification of GRBs, scientists primarily studied supernovae as the endpoint of stellar evolution for heavy stars, but GRBs have opened up a new chapter in this story. Gamma-ray bursts are not only extreme events, but also provide a glimpse into the core physics of stellar collapse. When a massive star collapses, it can emit enormous amounts of energy in the form of gamma rays, which are the most energetic form of electromagnetic radiation. This process is often linked to the formation of a black hole or a neutron star. The energy released during a GRB can be equivalent to that produced by our Sun over its entire lifetime, but emitted in just a few seconds. This tells us that the internal mechanisms of these stellar processes are extraordinarily complex and energetic. Moreover, the discovery of GRBs has implications beyond our own galaxy. We now know these explosions can occur at vast distances and are observable across the universe. By studying these distant bursts, astronomers can learn about the conditions and processes of star formation and evolution in different cosmic epochs. For instance, some GRBs have provided insights into star formation rates in the early universe, shedding light on how stars and galaxies evolved after the Big Bang. Gamma-ray bursts have transformed our picture of stellar evolution, revealing that the fates of massive stars are more diverse and intense than previously thought. They highlight the interconnectedness of cosmic events and the continuous cycle of birth and death in the universe. The study of GRBs not only helps us understand the life stories of stars, but also paints a broader picture of the universe's history and the remarkable processes that shape it. A rogue planet is a celestial body that wanders through space without being tethered to any star. Unlike typical planets that orbit a sun, these planets have either been ejected from their original solar systems or formed in isolation in the vastness of the cosmos. Estimates suggest there could be more rogue planets in our galaxy than stars, creating an intriguing idea that the universe is filled with these free-floating worlds. What makes rogue planets particularly fascinating is their mysterious nature. Without a sun to provide warmth and light, these planets can become extremely cold and dark. They may not have the same kind of geological or atmospheric activity that planets in a solar system experience, which adds to an aura of isolation and the unknown. Scientists often wonder about the conditions on these planets. Could they harbor life in some unexpected form? Or are they entirely barren, devoid of warmth and atmosphere? Rogue planets also challenge our understanding of planetary formation and dynamics. The traditional view posits that planets form in stable orbits around stars. However, the existence of rogue planets suggests that the processes of planet formation and interaction are far more complex. For instance, these planets could have once belonged to a larger solar system, only to be flung out by gravitational encounters, making us rethink what conditions foster the birth of a planet. The very idea of wandering worlds taps into a deep-rooted sense of mystery and exploration. With each discovery of rogue planets, we are reminded of the unpredictable dance of cosmic forces at play in the universe. Every rogue planet we identify invites us to ponder not just its story, but also the stories of countless more hidden in the ocean of stars. Rogue planets, those elusive wanderers drifting alone through the vastness of the galaxy, are both fascinating and challenging to detect. Unlike stars or planets that orbit a star, rogue planets do not emit their own light. Instead, scientists often rely on indirect methods to spot these elusive celestial bodies. One primary technique is gravitational microlensing. Gravitational microlensing occurs when a massive object, like a rogue planet, passes in front of a distant star. The intense gravitational field of the rogue planet can bend the light coming from that star, creating a temporary increase in brightness. Scientists carefully monitor many stars in our galaxy, looking for fleeting changes in light that might indicate a rogue planet's presence. This technique can even detect planets that are located several thousand light-years away from us. Another approach incorporates infrared observations. Rogue planets, despite not being tied to a star, can still emit some heat left over from their formation. Scientists use powerful infrared telescopes to locate these warm objects in the darker regions of space. They can identify these planets by measuring the infrared radiation they emit, helping to confirm their existence even without the aid of a parent star. Moreover, advancements in observational technology have led to the discovery of more rogue planets in recent years. With the ability to analyze large datasets from surveys, astronomers can enhance their search for these lonely travelers. Each rogue planet found not only increases our understanding of the diversity of planetary systems, but also raises intriguing questions about how these worlds came to wander alone, hinting at the dynamic nature of our universe. Rogue planets are fascinating celestial bodies that drift through space without being tethered to any star. These planets might have formed in the traditional way, circling their parent stars, but for some reason, they were ejected into the vast, dark expanse of the cosmos. This phenomenon raises compelling questions about the conditions that might support life beyond our solar system. The implications of rogue planets for the search for extraterrestrial life are significant. Firstly, these planets could potentially harbor subsurface oceans or other forms of liquid water protected beneath thick ice layers. If such conditions exist, they would create an environment where microbial life could survive, even in the absence of a nearby star. Rogue planets could act as isolated worlds, preserving the potential for life in a way that is independent of stellar influence. Moreover, rogue planets may also provide clues about the cosmic evolution of life. If these planets were once associated with a vibrant, life-supporting system before being cast out, they may carry the remnants of their origins. This suggests that life could be more adaptable and resilient than we once believed, thriving in diverse and extreme environments, and evolving on planets that wander far from the familiar warmth of stars. Finally, the discovery of rogue planets expands our understanding of the distribution of habitable environments in the universe. Each new rogue planet we identify might challenge our preconceived notions of where life could exist. This means that the search for extraterrestrial life may not be limited to those areas typically associated with stars, but could extend to these wandering worlds, letting our imagination and scientific endeavors reach further into the cosmos than we ever thought possible. Imagine a planet drifting through space, untethered by any star. This is what we call a rogue planet, and while they may seem distant and isolated, their journey across the cosmos can have profound implications for the stability of our solar system. Over time, a rogue planet could enter our solar system's vicinity, potentially disrupting the delicate balance of gravitational forces that govern the orbits of the planets. One significant threat posed by a rogue planet stems from its gravitational influence. As it approaches, it could alter the orbits of objects in the outer solar system, notably the icy bodies of the Kuiper Belt and the Oort cloud. This shift could send long dormant comets hurtling toward the inner solar system, increasing the risk of collision with Earth or other planets. Such impacts could lead to catastrophic consequences, including climate disruption or mass extinction events. Moreover, the sheer mass of a rogue planet can have unforeseen effects on the planets closest to it, particularly the gas giants like Jupiter and Saturn. Their powerful gravitational fields could either capture the rogue or deflect it away, but not without consequences. The interaction might provoke changes in the orbits of our own planets, possibly leading to a chaotic reshuffling of celestial bodies over millions of years. Audiences might wonder, could rogue planets be a common occurrence? Absolutely. Scientists estimate that rogue planets could outnumber stars in our galaxy. So while they may pose a long-term threat, they also offer a glimpse into the dynamic and unpredictable nature of the universe. As we continue to explore the cosmos, understanding these wandering giants becomes essential in safeguarding our own celestial neighborhood. The fascinating world of rogue planets presents a captivating mystery in the broader field of astronomy. Rogue planets, which are worlds that drift through space without being bound to any star, come into existence through several theories that hint at the complex dynamics of planetary formation and evolution. One prominent hypothesis is that some rogue planets formed in the early stages of stellar systems, much like regular planets. They could have begun their journey in a solar neighborhood, forming around a star, and over time could be ejected into interstellar space due to gravitational interactions. Another intriguing scenario suggests that rogue planets could arise from catastrophic events within their parent star systems. For instance, during the chaotic formation phases, interactions between multiple forming planets can lead to ejections. Imagine a cluster of young gas giants, their orbits destabilizing as they interact with one another, leading to a scenario where one or more planets are flung away into the void, never to return. Such violent events could easily account for a significant portion of the rogue planets we observe today. Additionally, there is the theory that some rogue planets might not always be solitary beginners. Instead, these planets could begin their lives as moons orbiting a larger gas giant, only to be expelled from their host when gravitational forces shift due to various reasons, such as the migration of the larger planet within its system. This process could lead to a moon transforming into a rogue planet, wandering through interstellar space, devoid of any stellar light. Considering the vastness of our universe, the potential for diverse origins of rogue planets only adds to their allure. Each drifting planet carries with it a story of dynamics, chaos, and survival, challenging our understanding of how planetary systems operate and evolve. With ongoing advancements in astronomical observation, the study of these enigmatic worlds continues to intrigue scientists, revealing more about the complex tapestry of the cosmos. Rogue planets, those mysterious wanderers that drift through the cosmos without a parent star, have a fascinating relationship with the stars they encounter. As these planets move through space, they can come surprisingly close to stars, leading to a range of interactions. When a rogue planet nears a star, the immense gravitational forces at play begin to affect both bodies. The planet can be drawn into the star's gravitational pull, changing its trajectory dramatically, or alternatively, the star's gravitational influence might alter the planet's course. If a rogue planet is captured by a star's gravity, it can become part of that star's system, joining the ranks of other planets. This introduction can have serious consequences for existing planet formation. The gravitational tug of the new arrival could lead to instabilities, causing shifts in the orbits of already residing planets, potentially destabilizing their paths. This might culminate in collisions or ejections of other objects within the system, creating a chaotic dance of celestial bodies. Conversely, if the rogue planet passes close enough to a star without being captured, it can still impart significant effects. The interaction might lead to a transfer of energy, especially if the planets have similar masses. This exchange can result in tidal forces that may cause noticeable changes in the star's outer layers. For stars that have inhabited inner planetary systems, such encounters could lead to alterations that make those environments hostile or create new conditions for life. Ultimately, the interaction of rogue planets with stars is a testament to the unpredictable nature of the universe. Each encounter tells a story of orbital dynamics, influencing the evolution of star systems and reminding us of the diversity and complexity of cosmic relationships. Each rogue planet's journey adds another layer to our understanding of the cosmos, showcasing the intricate dance of creation and destruction inherent to the universe. Rogue planets are truly fascinating celestial bodies. Unlike traditional planets that orbit a star, rogue planets wander the cosmos freely, untethered by any star's gravitational pull. This independence gives them a unique trait. They exist in isolation, drifting through space. It's estimated that there could be billions of these orphaned worlds in our galaxy alone. One of the most striking characteristics of rogue planets is their formation. While many planets form within a protoplanetary disk around a star, rogue planets might originate in similar ways, but are later ejected during violent gravitational encounters, such as collisions with other large bodies. This tumultuous journey sets them apart, as they can emerge with varied sizes and compositions, often resembling anything from gas giants to icy worlds. Temperature is another remarkable feature. Since rogue planets do not receive heat from a nearby star, many of them are incredibly cold. They can reach temperatures that are just a few degrees above absolute zero, which makes them daunting environments. However, some may retain heat generated from their formation or from radioactive decay, potentially allowing for a unique set of chemical processes and conditions. An intriguing aspect of rogue planets is their potential for hosting life. While this may sound unlikely given their cold and dark surroundings, some scientists speculate that if these worlds possess subsurface oceans similar to those believed to exist on moons in our solar system, they could maintain a suitable environment for life. This leads to the captivating idea that life could exist in places we traditionally overlook, wandering as freely as the rogue planets themselves. The potential discovery of rogue planets, those wandering celestial bodies that drift through space without being bound to any star, has raised significant concern among astronomers. These planets defy conventional understanding. While most planets, like those in our solar system, orbit stars, rogue planets lack such anchors. Their existence suggests that the universe might harbor far more planets than previously thought, many of which are isolated and could, in theory, harbor life in hidden environments. One of the alarming implications of rogue planets is their unpredictable nature. Since they do not have a star's gravitational influence, their paths can be erratic. They can wander through galaxies, potentially colliding with other celestial bodies or disrupting the orbits of nearby stars. This unpredictability creates challenges for celestial navigation and studying planetary systems. It raises questions about the stability of systems we are currently observing, where a rogue planet might intrude unexpectedly. Moreover, rogue planets might possess environments that are entirely different from what we know. They could retain heat from their formation or have internal geologic processes that sustain subsurface oceans. The prospect of such hidden worlds challenges our definitions of habitability and raises the tantalizing possibility that they could host some form of extraterrestrial life. However, the vast distances and lack of illumination make them incredibly difficult to study. Finally, the existence of rogue planets invites us to rethink our understanding of planetary formation and evolution. How do these planets come to be? Are they ejected from their star systems due to gravitational disturbances, or do they form independently in the vastness of space? These questions drive researchers to explore and redefine what we know about the universe, reminding us that in our quest to understand the cosmos, new discoveries can often lead to more mysteries. Rogue planets are fascinating celestial bodies that drift through space without being tethered to a star. Recent research suggests that there could be billions of these worlds wandering through our galaxy, far away from their original planetary systems. This realization prompts a profound shift in how we understand the formation and evolution of planetary systems throughout the universe. Firstly, the existence of rogue planets challenges the traditional view of planetary system stability. Many models of planet formation assume that planets are formed and remain bound to their stars, but rogue planets introduce the idea that some may be ejected from their systems due to gravitational interactions. This opens up new questions about the processes that lead to planetary ejections and the dynamics of early planetary system formation. It suggests that our solar system, like many others, may have once harbored more planets than we currently see. Furthermore, rogue planets could provide insights into the possibilities for life beyond our solar system. Since they are not reliant on a star for warmth, these planets might possess internal heat generated by radioactive decay. This raises intriguing possibilities for subsurface oceans or even ecosystems thriving far from sunlight. As we continue to explore these worlds, we may find that life could exist in environments we had previously deemed inhospitable. Lastly, the discovery of rogue planets emphasizes the need for updated models of galactic evolution. With the sheer number of these planets potentially outnumbering those in stable orbits, they could significantly influence cosmic events, such as the interactions with other celestial bodies. Understanding the role of rogue planets in the universe enriches our knowledge of cosmic phenomena and helps astronomers refine their theories about the formation, life cycles, and interactions of planetary systems across the vast cosmos. Cosmic voids are immense regions of space that contain very few galaxies, resulting in vast expanses that seem almost empty when viewed against the backdrop of the more densely populated areas of the universe. To understand them more deeply, think of the universe as a vast cosmic web, where galaxies are interconnected by filaments of dark matter and gas, creating clusters and superclusters. The voids represent the spaces in between these structures, often measuring tens to hundreds of millions of light-years across. The unsettling nature of cosmic voids comes from their magnitude and the questions they raise about the composition and fate of the universe. These regions can be so expansive that they might make one ponder the implications of nothingness on such grand scales. Unlike a vacuum we might experience on Earth, cosmic voids challenge our perceptions of reality by existing as large, nearly empty spaces, making up about 80% of the universe's volume. This notion becomes even more intriguing when we consider the invisible components that fill the universe, such as dark energy and dark matter, which we cannot directly observe. Further adding to the intrigue of cosmic voids is their role in the universe's evolution. They influence galactic formation and distribution, impacting how galaxies cluster together and how they interact. The presence of a void can affect the gravitational influences that shape neighboring galaxies, leading to a complex dance that illustrates the interconnected nature of cosmic structures. While voids might appear as mere emptiness, they are anything but simple. They deepen our understanding of cosmic dynamics and challenge our ideas about what constitutes the universe as a whole. The mysteries surrounding cosmic voids keep scientists and astrophysicists engaged, as each discovery provides a new piece in the ever-expanding puzzle of our universe's structure and history. Cosmic voids are vast, nearly empty regions of space that make up a significant part of the universe's large-scale structure. They are formed through intricate gravitational processes over billions of years. Initially, the universe was a hot, dense soup of particles. As it expanded, slight fluctuations in density allowed matter to clump together, forming galaxies and clusters. The areas where less matter congregated, however, evolved into these relatively empty voids. These voids can span tens of millions of light-years across and contain very few galaxies compared to denser regions. Their formation is linked to the growth of cosmic structures. As gravity pulls matter into filaments, long strands of galaxies and galaxy clusters, what remains in between are these voids. This process illustrates the universe's dynamic nature, where dark matter plays a crucial role as it guides the formation and movement of visible galaxies and their clusters. Understanding cosmic voids is essential for cosmologists because they offer insights into the evolution of the universe. They help scientists analyze how matter is distributed on a large scale and provide clues about the mysterious dark energy that is driving the universe's accelerated expansion. Interestingly, the properties of these voids can reveal how space itself is structured and how galaxies interact with one another over cosmic time. Moreover, the existence of voids highlights the universe's unexpected complexities. Researchers have discovered that voids are not just empty spaces. They can influence the behavior of galaxies and cosmic rays, contributing to a broader understanding of cosmic phenomena. By studying cosmic voids, scientists unlock secrets about our universe's history, its present state, and its ever-evolving future. Cosmic voids are vast, largely empty spaces that make up about 80% of the universe's volume. In contrast, densely populated regions, often known as galaxy clusters, are teeming with galaxies, stars, and other celestial phenomena. The gulf between these two regions illustrates the universe's intricate structure and continuous evolution. The contrast in density is striking. In densely populated areas, millions of galaxies can be found within a relatively small area, bound together by gravitational forces. These regions can sometimes reach temperatures in the millions of degrees, partly due to the dynamic interactions between galaxies and the presence of hot gas between them. This energetic environment gives rise to a variety of fascinating phenomena, including the formation of new stars and even supermassive black holes at the centers of galaxies. On the flip side, cosmic voids can be surprising in their emptiness. They can span upwards of 100 million light-years across, often containing only a few galaxies or none at all. The extremely low density of matter in these regions hints at the universe's grand design and is believed to play a critical role in guiding the overall structure. Researchers even suggest that these voids influence the motion of galaxies, creating an intriguing cosmic dance across vast distances. Moreover, the interactions between cosmic voids and densely populated areas contribute to the phenomenon of gravitational lensing. This effect occurs when light from distant galaxies bends around massive objects, providing vital insights into the distribution of dark matter. The stark dichotomy between voids and rich regions illustrates not just the complexity of cosmic architecture, but also our ongoing quest to understand the fundamental laws governing the universe itself. Cosmic voids are immense, almost empty regions of space that exist between galaxies. These vast expanses can stretch for hundreds of millions of light-years and contain very few galaxies, stars, or other matter. Despite their emptiness, cosmic voids play a significant role in the structure of the universe and can profoundly impact gravitational forces. One of the most intriguing consequences of these voids is how they influence the overall gravitational landscape of the universe. Since gravity is a force that attracts matter to itself, areas with less matter, like cosmic voids, exert a weaker gravitational pull. This means that where voids are present, the gravitational forces can be reduced. Consequently, galaxies and galaxy clusters are often found at the edges of these voids rather than in their centers. This arrangement leads to a fascinating cosmic structure, often likened to a web, where galaxies trace the filaments of denser regions, while voids delineate the emptiness in between. Furthermore, the presence of voids influences the motion of galaxies. As galaxies travel through the universe, they tend to be drawn toward regions of greater density, like the cluster formations that sit at the edges of these voids. This interplay of attraction creates a dynamic where the gravitational pull can create streams of galaxies moving toward one another while avoiding the empty spaces of voids. Over cosmic time, this movement helps shape the larger structures we observe in the universe today. Cosmic voids are not just empty spaces, they are active participants in the cosmic ballet of gravitational forces. By creating zones of lower gravity, they guide the motion of galaxies and help define the structure of the universe, giving us profound insights into how everything from small galaxy groups to massive clusters is connected within the vast tapestry of the cosmos. In the vast tapestry of the universe, scientists have uncovered intriguing structures known as cosmic voids. These expanses are massive regions of space that are remarkably empty, with far fewer galaxies than we observe elsewhere. To map these voids, researchers employ advanced techniques, often using data collected from large astronomical surveys. These surveys compile information from telescopes that scan the night sky, capturing light from distant galaxies across various wavelengths. One of the key methods involves analyzing the distribution of galaxies. By observing where galaxies cluster, scientists can identify areas of relative emptiness, those cosmic voids. The use of three-dimensional space visualization helps illuminate how these voids are situated within the cosmic web, an intricate arrangement of matter in the universe. This network consists of filaments of galaxies and clusters intertwined with vast voids that can stretch tens of millions of light-years across. Recent discoveries reveal that these voids play a significant role in shaping the universe. For instance, researchers found that voids can influence the motion of galaxies. As matter collapses into denser regions around these voids, the dynamics can accelerate the growth of structures in the universe. This has led scientists to reconsider how galaxies interact and evolve over cosmic time, providing insights into the life cycle of the universe itself. In addition to their role in the cosmic web, voids hold clues about the nature of dark energy and dark matter. Since these mysterious substances make up the majority of the universe, studying voids enables scientists to probe the fabric of reality itself. The more we learn about these emptinesses in space,